All right, scholars, today we're going to do 2.2 change in linear and exponential function. So quick reminder of what things are. Last lesson we learned about arithmetic sequence and geometric sequence. Arithmetic sequence is when the same number is being added and that number is called a common difference. Geometric sequence is that same number is being multiplied, r, and that's called a common ratio. And we also learn how to plug it in to find the nth term, or find the equation, the general formula for those. All right, so you're supposed to do this by yourself, but oh well, I'm here, so let's just do it. The greeting card selection are regularly updated and new display are set up each season. There you go, you don't really need to know it. Gary has already stocked 3 packages by the time her shift officially starts. So at 0 time, she has 3. Additional information about the number of packages she has stocked at various times is given at the table. So first thing I notice is the x is increasing and is increasing the same interval. You see that it's increasing by 0.5, which is very important that you note that first. Now let's look at what happened to the number of packages. I noticed that it's been increasing by 35 each. And then how much is your n is increasing? 0.5. each. Okay, what do you notice about information at the table? Describe any pattern you see. I see that number of packages stuck is going up by 30 packages every half an hour. So you're adding 35 packages every half an hour. Yeah? All right, at what rate is Gary stocking up the packages? When we usually talk about the rate, we don't really say per half an hour. We like to say per hour or so. So per hour. So if you look at per hour going from 0 to 1, 1 to 2, how is it increasing? 3 to 75, 70, 75 to 143, 70. Because you just have to add these two, right? So increasing 70 packages per hour. Now, write an equation, number of packages Gary will have X hour after her shift begins. Why does it look like that? There we go. It's a little better. Alright, so before we go on, when I say 70 packages per hour, that sounds more like a slope, right? Doesn't it? Like something per hour, something per hour. So, I'm going to think of this 70 as a slope. Are you good? Well, then when I come up with the equation, how am I going to do it? All right, a few things that I want you to know. In Algebra 1, when you know a point, x1, y1, and you know a slope, you learn this formula. You learn that point slope form. This is a point slope form. Okay, so you just have to take that one point that you know, plug it in x1 and y1, and then slope m goes in there. So that's what I'm going to use. Why? Because 70 is a slope, and we have lots of points you can plug it in. I'm just going to plug that 0, 3 in. That 0 is your x1. That 3 is your y1. Okay, let's plug it in. So I got y is equal to y1 plus m x minus x1. What was the y1? 3. What was the slope? 70. X minus x1 is 0. Ooh, then I got 3 plus 70x. Y is equal to 3 plus 70x. What do you notice? That's a linear function. Now, I'm going to stop for a second. Do you remember us going over this formula last class? Let me write it like this. A sub n equal to a sub k plus d n minus k. Remember doing that? Yeah? And then I was like, oh, that's too hard. Let's just stick with a sub n equal to a sub 1 plus d n minus 1. And we use that more on our Delta Math and other assignments. Yeah. Do you wonder where that came from? Say yes. Yes. Actually, that's like a twin of this point slope form. Well, how are they similar? Folks, that slope m of a linear function is same as that common difference. We learned it last class, so that should not be a surprise. Now, for this one, we use a point x1, y1. And x1 goes here, y1 goes over here. Where does x1 go? 1. Which one are we using for y1? a sub 1. So that's actually a point, right? 1 comma the first term. And then the n in a sub n is just generate input n and then output a sub n. So they're like the same thing. We're just using different letter because for the linear function we use x and y. For arithmetic sequence we use n as an input, like whole number, right? And a sub n as an output. So they're the same thing. So that's where this whole thing came from. Yeah, we'll talk more about it when we summarize it later. All right. If Gary has a stock 150 packages, how long will it take her? So the 150 is equal to 3 plus 70x, 2.1 hours. That one's just simple, easy. All right, now we're changing gear up a little bit. The greeting card is declining. So in 2010, 6.5 billion, and then between those decrease at approximately 2.8% per year. All right, so are we decreasing the same amount? Like, does it decreasing like thousands every year? No, it's decreasing same percentage. Okay, all right. So when it's decreasing the same percentage, I can probably assume that that has something to do with the exponential function. And since we're dealing with the exponential function, if you want to write that as a sequence, it's probably going to be with type of sequence? Geometric sequence. Okay. All right. According to estimate, how many greeting cards were purchased in 2011? So in 2020, excuse me, there's 6.5 billion. In 2021, how many is it going to be? So decreasing 2.8%, that means we have what? 97.2% of that previous year, right? So if you have 97.2% of this, remember how to do the percentage? You move to decimal, so you multiply 0.0972 from 6.5 billion to get to the next, which I believe is 6.318 billion. Okay, in fact, I made a table over here on the next page, and I fill it all out for you. Okay, so what was it? It's decreasing 2.8% from the previous year. That means you're multiplying it 0.972. You with me? I'll explain that one more time. Decrease 2.8% means you're left with 98.2%. So you multiply 97.2% from the previous year to next, and next, and next. You good? All right, so since I'm multiplying a ratio, I can think of 0.972 as the common ratio. Yeah? All right, skip number 7. Go to number 8. Write an equation for the number of annual gathering purchase after 2018. How are we going to do it? How do we do the exponential function? Well, geometric series. You can think of either way. Let's do the geometric series. Why not? So we learned that G sub n equal to G sub k times R n minus k. Remember that from last class? Well, but then we were like, this is too hard. Let's just stick with G sub 1. And this is what we use. You all remember that. Okay, now let's plug it in. G sub 1 is the first term. Be careful over here, because what's the first term? 2018 is 0. That's when you start. So the first term is actually going to be 6.687. Right? Because this is t is equal to 1. This is t is equal to 1. G sub 1 is the first one. So this is 6.687 times, what was the R? 0.972 raised to the n minus 1 power. All right. One thing you remember from the last lesson was that you should not probably leave it like this. Then what am I going to do? This is same as, this is a good review. That is same as 0.972 to the n power times 0.972 to the negative first power Remember that you split that up, and then that is same as 6.687 times 0.972 to the n power times 1 over 0.972, because negative exponent makes it flip it like that. Then I get 6.880, 0.972 to the n power is what I get. Okay, please be careful with that negative thing going on. Wait a second, have you seen 6.880? Right here, that's the value when you started. Wait, so what am I saying here is that this is actually same as the g sub 0. That's the first initial term times r to the n. Isn't that what I'm saying here? Right? Because this one was when we were using g sub 1. When I use g sub 0, the initial value, I get this. Wait a second. Right there. Look at that. So if you don't want to use the first term, you can actually use the initial value of geometric series, g sub 0 times r to the n power. Isn't that cool? Say yes. Alright, so that's, I just wanted to go over it quickly. Arithmetic sequence is very similar to linear function. There's a common difference. You write it down. Yeah. And then geometric sequence is very similar to the exponential function. Exponential function, you can come up with it, and yada, yada, yada. Alright, now let's actually look at the lesson and learn it.